Welcome everyone to this 18th session on statistical learning in practice. As I was just saying, we'll see nearest neighbors classifiers today. So let's get started, and it should be, I hope it is a bit shorter than the previous ones, so that we make up for slightly longer sessions. So 2 to 3 nearest neighbors classifiers. And we're going to start with the classical k nearest neighbor classifier. So that's 2, 2, 3, 1, and k nearest neighbors classifier. So I will shorten this by KNN. And you've, some of you have probably seen this one. So let's just recall what it is about. So training, imagine that we have some training data that we're going to represent by x1, y1, up to some xn, yn, so just as usual. And we're going to place ourselves in the setting in which the covariates are in some p-dimensional Euclidean space, on the p-dimensional Euclidean space. Okay, so then given this data, for a given x in this space, right, we wish to classify it. And so how do we do that? Well, what we're going to do is just to take the nearest, in this case, the k nearest neighbors, and we're going to look at the labels and just do a majority voting. Okay, so then let x1, and now this is, the notation is a bit different, as you can see. So the subscript has some brackets, and we'll see in a sec what that means. So this is a, so let this be a permutation of the data such that the first element in that permutation, what it means is that its distance is actually the smallest among all distances to x, okay, of all of the training data points, and so on. So what we've done essentially is to order them according to how far or close they are to the x. Okay, so and maybe I will add this in the remark later, what I was going to mention now. So let's then, given this, introduce the definition of the classifier. So definition 17. The k and classifier, and k of course must be less or equal than n, is, this will make sense in a second, is the argmax over L of this quantity and this is of the, so let me comment on this. Okay, so this is the definition. Okay, so what is this saying? Well, it's clearly saying that we wish to look at the k nearest neighbors and then look at the proportion of them that have a given label L, and then we'll take the largest proportion as the label that we assign to this given x, right? So it makes perfect sense, right? So in many occasions, you in the definition you won't see this guy, this 1/k, but I like to introduce in the definition. I mean, it of course doesn't make a difference whether you include it or not, because this is a constant in terms of L, so you could take it out. But I think it gives a bit more coherence to the whole section, because it, it's sort of, this is a, I mean, it's essentially a probability, right? So then I like just keeping the quantities being the probabilities, because we'll talk about probabilities in a second. Okay. Okay. So as I just said, the k nearest neighbor classifier is going to classifier classifies x via a majority voting, right? Scheme among, of course, the k nearest neighbors. Yeah? Okay. So okay. Then the second remark, which is related to this, to writing the classifier in terms of probabilities, is that k and n estimates the regressors eta x1 up to eta x capital L by these probabilities, right? So these guys here. Right. And note that I think it's probably the first time I've said that it estimates, that a classifier estimates and not really that it models, right? Because this is not really a modeling assumption, because we already have the data. So this is an estimation. So while before, when I was introducing classifiers, I was just first of all saying, well, we model this via this function of the input that depends on certain parameters. And we've been seeing, classifiers that were getting more and more complex, whose, number of parameters probably was increasing, such as neural networks compared to linear classifiers. And then we sort of tried to look for the best parameters, or the parameters that would give us a best fit, according to some loss function. But that's not really what we say here. So here we just say, well, we'll estimate it via this empirical quantity, and then let's try to work out what the modeling assumption is, resulting from this estimation, or approximation. So, let's do a thought experiment. What we have is that if we had, several data points with the same covariates value, so with the same x, then what we would be doing is assuming that the label that came out most often is the one that is going to correspond to the given covariate, right? And that sounds pretty reasonable, right? As an assumption. But of course, the covariates generally tend to be different between data points. If you were to look at them, from from the perspective of them being random, then they generally correspond to a continuous distribution, or they come sampled from a continuous distribution, and therefore, we're never going to fall on the same, sort of value of the covariates again and again. And in fact, we won't have values of the covariates for every single x in the Euclidean space, Rp, right? So what is the assumption then? Well, what the assumption is that if you are at a given x, in a neighborhood of it, basically you're going to be, except for the case when there is a boundary, but if you're a bit away from the boundary, then what you're assuming is that in a small region, the function is constant, right? So what we have is a piecewise constant assumption, yeah, at least for finite data, right? And as we let the data go to infinity and it sort of fills up the space, what we have is that what should be happening is that we can approximate the boundaries and the resulting sort of I guess function of the covariates that gives you the labels via these sort of piecewise constant approximations, yeah, so that we can approximate it well in that sense. So so this assumes essentially some regularity on the boundaries, and this is now in the territory of non-parametric statistics, and this is a bit of an implicit assumption, okay? Okay, so let me just write in words briefly what I've said. So what we have here is the K and N's modeling assumption. Is that the regressors can be approximated well via piecewise constant functions, right? Okay, so that sounds like a pretty reasonable assumption. So let's see if we can have some. Oh, actually, so I was going to make another remark before when I introduced the definition here. So let me maybe say a few words about this, and is that, so here we've assumed the L2 norm, right? When actually it may not be the best norm to have. So for instance, if we have strings, we may wish to look at the number of elements or the number of entries of the string that are different. And so we may use the Hamming distance, for instance. And when we have images, the L2 norm may not be the best one, because it may be that, because that doesn't account for the fact that an image should be classified as the same thing if, for instance, we translate it within the window of pixels, right? Or if we rotate it and so on, yeah? So we would wish to account for such invariances via the norm, and this is not actually an easy task. Okay, so generally what is done, rather than trying to design this norm very carefully depending on the transformations that you want to have invariance with respect to, is just to augment the data set with the data in such a way that what you wish to be invariant, you assign it the same label. Okay, so for instance, if you have an image, then you rotate it and still keep the label, and then add that to the training set. Okay, and this is what we'll do in the practical, and this is generally what is done. So then, with that, you basically account for this, or you embed the invariances that you want in a very, very simple way. Okay. So let me maybe just say very briefly. So 3. Depending on X and the application, we may use different norms for the ordering. What am I writing? Ordering. Or even, okay, it's not going to fit, so let's just go to the next. Or even different strategies. So C practical. Yeah. Okay. So I would say in that, after the second remark, I said that we wish to have some theory, because obviously this is quite an intuitive classifier. So let's then just introduce one definition, and then we can introduce a result. So let's say that, so if this psi is a classifier trained from n data points, we define its risk as R subscript n now. So that's what, how it is different notationally. And this is the expectation of the indicator of this guy being distinct from Y. Okay, so this is just the probability, therefore, of this guy being distinct from Y. Yeah, and what is important is so where this guy and this guy are with respect to the data, so the n data points, and also with respect to xy. So what I mean is that the integral that you would have here is n+1 dimensional. Okay. So the measure that we are integrating with respect to is just the product. Well, if we assume independence, is the product measure for all of the distributions of each of the pairs. Yeah. Okay. So then theorem 6. Okay. So we have that the risk of the base classifier. So I remind you that this is the classifier with least risk for a given pi. So we are implicitly assuming that there is a given pi. prior. This is bounded as the limit and goes to infinity of the risk of our nearest neighbor classifier, but of the one. Okay, so the one that uses only one neighbor. And this guy is in turn bounded by 2 times the previous risk minus L minus 1 of the risk, again, of the base classifier. Okay, so this is giving us control, at least asymptotic control of the risk. And so let's make a couple of remarks. So the first one is, what we conclude from here is that certainly the risk of this one nearest neighbor is between the risk of the base classifier and 2 times the risk of a base classifier. But actually this can be, this can be quite tight, the space that you have between the 2 bounds. And certainly, if we only focus on the 2 times the risk, well, that's reassuring, right? Because what we're saying is that at least half of the information to classify data points is contained in this, in actually the nearest neighbor. Okay, so this is reassuring, what I'm now saying, reassuring. But there's a big but here, misleading. Yeah. So this is akin to, the result that we saw in neural nets, in which we were looking at shallow networks, and we said that they are universal approximators. And again, that's reassuring because you certainly wish it to be a good approximation, but misleading in that in practice that's not really what is happening. Yeah, that they are good approximators. So this is misleading for finite. When I say in practice, I of course mean finite samples. Okay, so finite samples or finite n. Okay, because the bias and variance actually let's say the variance and the so the variance, certainly variance and partly the bias are large. Okay, or is, sorry, because I'm not, is. Okay, so we have, there is not, finite samples is not, let's say maybe here of 1 and n, so that we make sure that we're talking about the same thing. Okay, so talking about bias and variance, let us then explore this a bit, depending on the k parameter. So what we have is that as we increase the k, let us maybe plot some data here, some, I guess, so let's see, what can we have? So let's say green, yellow. Okay, so we have Oh, that's not very good. Orange. Okay. And then let's say some green. I'm attempting to have the same data on both, yeah? Okay, so if we have the k equal 1 nearest neighbor, what's going to happen is that, maybe when we're here, we have this line, but then we'll start sort of trying to classify things according to, sorry, now the green bit disappeared, and that's important to see it. And so, what we'll have is some, actually, maybe that we have something a bit different, I feel. So let's just take something like this. I'm not 100% sure that this is exactly what we would get, but approximately would be something of this kind, yeah? I mean, I'm not trying to compute it in my head, as you can imagine. Okay, but we would get something like that, yeah? So we'd see that, these three regions there, generally, we'll classify points near these other points as green, but it's not really very satisfactory, yeah? Then if we're increasing the number of neighbors, then maybe we'll do something like this. And if we have, so this is k larger than 1, and this is k much greater than 1, yeah? So what we'll get is that it will be simpler and simpler, yeah, the classification boundary. And so what we're getting is that as k increases, the variance is going to decrease. Yeah. And the bias is going to increase. Yeah. So why is this? Well, sort of intuitively, you can look at it in two ways. So the variance, given the definition of our classifier, which is here, well, if we're taking an average of more and more points, then of course the variance is going to be smaller and smaller. Yeah. Or also the variance in a classifier more generally, without really looking at the expression, is or can be interpreted intuitively as the as the sensitivity to changes in the data. Yeah? So, of course, if the data changes a bit in the k equal 1 case, well, the classification boundary may change. So that means a lot of variance, and the other way around in this case. So what we see here is nearly a straight line, and if a point changes, then that straight line is actually very robust to the data. Yeah. So we have low variance. And in terms of bias, the bias is the complexity of a model, or which is, well, the bias is the ability to explain the sort of underlying data generating mechanism in a data-less sense. And so, of course, the more complex the model is, generally, not always, but generally, the lower the bias. And And that's exactly what we see here, right? So the classification boundaries for this guy are much more complex, so they can adapt to boundaries that would be more wiggly or less regular, while in this case they wouldn't be able to adapt to very complex boundaries. Yeah. Okay, so I'm now stepping on over my words of saying this may be a quicker session, so let's move on. So okay, so there is the question of how do we choose k then? Yeah, is there an optimal k, if at all one? So let me just mention that under some assumptions, the mild assumptions, we have that k star of the order of 4 over p plus 4, and this is asymptotic. Yeah, so I'm saying this is the order, is optimal. And this is under some assumptions of regularity assumptions on the boundaries, on the classification boundaries. But in practice, I mean, because this is only the order, right? So we're missing the constant. We don't know the constant generally in practice. So in practice, you can, you probably expect what we do, right? We choose k via cross-validation. Okay. Okay. So let's now move on to the next type of nearest neighbors classifiers. So this is 2232. And this is bagged and weighted nearest neighbors. Yeah. Wow, let me shorten this. Classifiers. So these are two types. Yeah. Okay, so let me define what I mean by bagged, and actually, it's actually the procedure of bagging. So let's fix some natural numbers, capital B and lowercase m. So then we say that the bootstrap. Okay, so what do I want to say? Okay, so the bootstrap aggregated or bagged. Okay, so this is short for bootstrap aggregated. So the bagged nearest neighbor classifier is defined as follows. So we have a few steps. So we have the bootstrap step, in which we have that for b now lowercase to the uppercase one, we're going to first of all sample some guys that we index by this lowercase b. We're going to have m of them. Okay, so this is where the M comes in. Sorry, that's Y. And we do so from the data, of course, from the training data that we had above. And we do so with replacement in the bootstrap procedure, of course. So we could do so without replacement, and we'll see that in the example sheet in the last one. And then B, compute the resulting one nearest neighbor classifier. We're going to call this guy this psi B. Okay, and then second, so of course we have one for each set of samples, of bootstrap samples, and then the aggregation step which says to define the bagged classifier as so this B, lowercase b, is not the previous lowercase b, but rather it stands for bagged. Okay. Okay, so this guy is the argmax over the L's of now the one nearest neighbor classifiers. Okay, so this is probably better to call it B. Okay, so just for clarity, what we are doing in the bagged nearest neighbor classifier is having a majority voting, but now between or among one nearest neighbor classifiers. And how do we construct these? Well, each of them comes from a bootstrap sample from the original data set, right? Okay. So let's make a remark about this. So remark. And of course, we wish to compare this to the one nearest neighbor classifier. Yeah. So there is one case that is special, and is that is the one when m is much less than n. So then what we have is that bagging in this case reduces the variance of the let's say directly of this guy. Well, okay, fine. Of the one nearest neighbor classifier considerably. Okay, but let's say maybe not as much as as the B and classifier, by which I mean, of course, to look at the capital B nearest neighbors, which is something that we could have done, right? Rather than averaging over, rather than looking at the majority voting of these 1 and n classifiers, we could have looked at just the majority voting among the capital B nearest neighbors. And that actually decreases the variance more, but we still need to think about the bias, right? So the bagged classifier increases the bias only slightly. Unlike the BNN classifier. So then the question stands, well, I can tell you that it is better than the BNN classifier. And so do we have any guarantees for the risk? Because it turns out that the risk is smaller than for the 1NN classifier. So yes, we do. So let me just introduce the result. So theorem 7. So under mild assumptions, we have that this guy, which is defined as the limit as b goes to infinity of the bagged nearest neighbor classifier. Well, now this guy is going to be the arg max over L of the following quantity. So now it's the sum, this guy times the y is equal L. Okay. And this is for some weights such that the sum, so these are just, 1. Yep. Okay. And the other thing we can say in the theorem is that for asymptotics, so for the asymptotics in which m goes to infinity with m over n going to 0 appropriately, so not for any, but just for some sequences satisfying this. We have precisely what I mentioned earlier, which is that we have some control of the risks. So this guy is less or equal than the Rn of the not only of the one nearest neighbor classifier, but actually of that which is carrying the optimal number of neighbors. Okay, and this is for p greater than or equal to 2, so not for 1, and we have strict inequality for p greater than 2. Okay, so we see that this bagged nearest neighbor classifier is actually better than the more intuitive ones, and also simpler ones that we introduced at first. Okay, but you probably have realized that they share something in common, right? Because we wrote it in this way now. Okay, so we have some weights here, and so did we with the k nearest neighbors, right? They were just very simple weights in which we were assigning equal mass to all of the indicators, right? So these, okay, so then what we can say here is that k and n and bagged nearest neighbor classifiers are what are called weighted nearest neighbor classifiers. Okay, which I can shorten by W and N. So these are of the form you can expect from above. So this is this guy being the argmax over the L of some sum of some with some weights of the same indicators that we had above. Yeah? Some okay. So let's now make a couple more remarks given this idea of weighted classifiers. So this guy that we introduced before turns out to not be optimal among all of the weighted classifiers. But it does converge to the let's just say to an optimal weighted nearest neighbor classifier as the number of covariates increases. Yep. Okay, and then the last remark is that any, let's say, K and N, well, any, let's see, yeah, let's, okay, classifier can be modified into a weighted nearest neighbor classifier to improve its risk. Okay.